static equilibrium and what we call the law of the lever. And we talked about torque in the last video. And based on that, I just wanted you to calculate the torque on this wrench, okay? So if you wanted to, it's kind of neat understanding how torque gives you a mechanical advantage, because if you picture turning a wrench, would you hold it here or would you hold it here? And the answer is you would hold it further back, right? That would give you more torque, and it would give you more ability, well, which gives you the ability to turn the bolt, right? So, but anyways, in this warm-up question, I just want you to calculate the torque. So I would, I think you should pause it, do it yourself, and then check your answer on the next page, but I'm going to move on. So here's the answer. Torque is just force times distance. So we have the 100 newtons force, we have the 20 centimeters, put it into meters, of course, right? 0.2 meters, and it's that simple. 100 times 0.2, so 20 newton meters. Okay, so keeping in mind that levers are simple machines, we remember that they do give us mechanical advantage because you can do work. In this case, our work is lifting something, right? By applying, that has a heavy mass, by applying a smaller force, depending on where you apply it. And I think the great example is, of course, the teeter-totter thing. You have two equal-sized kids, okay, they both go on the end of the teeter-totter, it's all fine, right? Now, if you got a heavy kid, say a grade 8 kid, and a grade 2 kid on the same teeter-totter, for them to be successful, because the torque has to be even between the two. So what you know from experience is the heavy kid's got to get closer to the fulcrum, to the center. And that's so that their torque evens out with the little kid's torque, right? And that sort of gives you an idea of how you can get mechanical advantage. It's kind of the same idea. That kid's little mass is good enough to lift the grade 2's little force, little effort, is good enough to lift the big kid if they're further enough away from the fulcrum. And that's how you get mechanical advantage to a lever. So we do everything using the term like static equilibrium, assuming that things are going to be equal. And then you make any assumptions further than that. And that gives us some equations. So static means something's not moving, and equilibrium means happy. And what I'm saying here is, if this is our teeter-totter, and here's our grade 6 kid, and here's our grade 2 kid, if this big kid was closer to the fulcrum, and this little kid was further away from the fulcrum, they could balance out, and you'd have what's called static equilibrium, where they're both in the center and it's not going up or down, right? At that point, you've got static equilibrium. And then, if you want to be able to, for the little kid to be able to lift the big load, then that little kid's either got to move a little further away, or the big kid's got to come in a little closer, something like that, so that you can sort of get greater than that static equilibrium. But we do all our calculations assuming you're looking for a balance, static equilibrium, which of course isn't always the case. So what I'm saying here, effort torque, so E means effort, has to be equal to load torque. And that's for a lever system to be in balance. And then just looking, if you remember the calculation, that torque is force times distance. Well, it's the effort force times the effort distance, and that's what I say here. This is, in this particular example, I'm saying this is my effort and this is my load. So imagine, again, you're trying to lift something really heavy. You want to put in a little bit of force to lift something really heavy. Well, to do that, the distance to the center, to the fulcrum, multiplied by the force you can apply, would have to be equal to the load distance, which is the distance from the load to the center, times the force of load, the weight of the load, right? And then all you do is apply just a tiny bit more, and you'll succeed in lifting it. And there's just the definitions of all the letters I used. Okay. I just wrote these out for you, these rearranged forms of those equations. So this equation here is our guiding equation for most of this unit relative to levers, okay? And I rewrote those in the different forms, and I think I just gave it to you. You don't have to copy it, because often what these questions are is sort of, you know, 3 of these things, you're asked to find the 4th. So this equation's to find effort force, that one's to find load force, load arm, effort arm, okay? And I think we'll do an example to practice that. Here's the teeter-totter. So you've got Frankie and, I guess this is my grade 2 or my grade 6 kid, Frankie and Joey on the teeter-totter. So here's Joey sitting 1.2 meters from the fulcrum. How close does Frankie have to move so that they can achieve static equilibrium? So when I say how close, you think, well, what am I looking for? Close is a distance. I'm looking for, you know, this distance here. And basically, you know, here I'm saying that's 1.2 meters. I want to find DL. We don't really, in this case, there's not really a load versus effort. It's not obvious that one person's lifting the other, but we're just going to call, Joey the effort and Frankie the load. And so Joey's effort is his mass times 9.8, so that's his weight, okay? And Frankie's the load is his mass times 9.8, okay? So we're looking for DL. So we know how far Joey's sitting. We want to know where Frankie has to sit for those two to be equal. Okay? So you just sub in into that equation. So this equation again would be written on the past page. So if you're looking for DL, you just get that equation and you sub in the numbers, the effort force, the effort distance, and the load force. And it's 0.74 meters or 74 centimeters. And therefore, for them to be evenly matched, that's where Frankie's got to sit. Okay, one more example. And this is more the idea of using your lever as a machine. Here the man is lifting this heavy rock, okay? And we know the mass of the stone and we know how far it sits from the fulcrum, right? The stone is 50 centimeters away from the fulcrum. If we know that the most this man can apply is 1,000 newtons, which would probably be about his weight, probably if he just sat on it would be the most force he could apply. How far away from the fulcrum does he have to apply it in order to actually lift that load, lift the rock? Okay, so just looking at, first of all, let's look at, looking at the data. So we know the mass of the load is 300 kilograms. We know the distance from the load to the fulcrum is 0.5 meters, and we know the most effort force he can put in is 1,000. So where's the DE got to be? Well, first of all, knowing the mass of the load, to find the actual load force, you multiply by 9.8. That's the first thing you do. Once you're done that, then looking for DE, you just find the equation with DE by itself, sub in the numbers, and it's 1.47 meters. So all he's got to do is apply his 1,000 Newton force, greater than 1.47 meters away. So if he applies it just at 1.47 meters, he can be equal, right? Then he pulls back a little bit further and he'll be able to lift the thing. Okay, so you can pause it there if you want to keep writing. I'm going to move on. Actually, that's it for the video. So that's it on static equilibrium and law of the lever.